Good afternoon, distinguished guests, ladies and gentlemen, and viewers joining online. Welcome to the 2024 10 Prize Master Forum in Sustainable Development. Today, we are honored to have with us our Master, Professor Omar Yaghi, the 10 Prize Laureate in Sustainable Development, for his extraordinary contributions to sustainable development with his pioneering metal, organic, and other ultra-porous frameworks. He will share with us his invaluable insights and perspectives on the development of these materials and their future prospects. To begin, I would like to invite the President of National Yangming Chiao-Tung University, Dr. Lin Zhihong, to deliver the opening remarks. Please join me in welcoming President Lin to the stage.
First, on behalf of NYCU, National Yangming Chiao-Tung University, I welcome all the guests, especially the Tang Prize Masters. Today is Tang Prize Masters Forum on Sustainable Development, which is certainly a very important issue. So welcome you all to NYCU. This is Guangfu campus, located in the original Chiao-Tung University. I just show Omar, the path of typhoon. It's right next to the Taiwan island. Actually, right now it's at the turning point, whether it's going to turn north right away or going to move west for maybe a couple more hours and then turn north. That makes a lot of difference. If it turns right now, we have the protection of Central Mountain, we'd be relatively okay. But if it's delayed for half a day, then the worst case scenario would be that it just follow the Taiwan Strait. That will cause a major disaster or catastrophe damage to Taiwan. I think some of the audience, including me, remember a long time ago we do have a typhoon take that path. But for most of the younger generation, will come to experience the power of nature. The reason I use this to open this this forum is that I think we need to respect the nature, okay? And the typhoon, the lesson that we are now experiencing and we're now about to take, teach us to respect the Mother Nature and the unpredictable behavior of unpredictable nature of the Mother Nature, of the climate changes, and we certainly need to find ways to really conquer and facing the challenges that we now are heading toward. So this event, of course, is co-hosted mainly by ITRI. Thanks the president of ITRI, Dr. Wu, who joined in organizing this forum with us. And also, I want to thank the organizer of the Tang Prize. We've been planning for this, and this is under the College of Engineering, and Dean Lin is really in charge of the entire processes. So I hope that you can take this opportunity not only to learn from what Dr. Yaghi can share with us, but also we have a beautiful lily pond just in front of the building. If the typhoon took the wrong way, then I'm afraid that a week from now, there will be nothing left, okay? So enjoy your stay. This is not only a fruitful event for your mind, but also I invite you to really take this opportunity to really enjoy the campus life of NYCU. So thank you and welcome.
Thank you, President Lin. Now, I would like to invite Dr. Wu Zhenzhong, Chairman of Industrial Technology Research Institute, to say a few words. Let's welcome Dr. Wu.
Professor Yaghi and President Lin, and also President James Liao from Academia Sinica, all the distinguished guests, ladies and gentlemen, good afternoon. 大家好. It's really an honor for ITRI, the Industrial Technology Research Institute, to co-host this very important forum for Professor Yaghi, and also on a very meaningful topic about the environment. And President Lin just mentioned about the typhoon, and we really hope that the Taiwan will choose a very good path, not disturb Taiwan a lot, and especially don't come to Yaminjiaoda. And also, because Italy is also around these regions, so it's very important to ask the typhoon don't come to Taiwan. Actually, for the past 8 years, not so many typhoons come to Taiwan, because when the typhoon reach Taiwan island, then it just turn away, just bring water to Taiwan. But this year, I think this typhoon is, it may come to Taiwan, so we have to keep alert. First of all, I want to take this opportunity to congratulate Professor Omar Yaghi for receiving this very big prize in Taiwan, Tom Prize. And it's really a great prize for Taiwan. From Taiwan, actually, it's sort of international prize. And we are really happy that we can have so many Tom Prize winners to come to Taiwan and to help us to distribute what we have in Taiwan currently. And this is, I think, the meaning of the Tom Prize. And because I'm not in this area, the material chemistry areas, although I was a professor in NTU, but my colleague, the vice president of Dr. Lee, he told me about that. Professor Yaghi, you did a great contribution to the materials chemistry for your lab in Berkeley, and especially for the invent the new models. He told me about the covalent and metal frameworks, organic frameworks. And that is very important for the future in saving the environment, especially for water retreat. And Professor Chen, he just told me that in the future, we don't have to have water plants outside. We just have a machine at our home, then you have a lot of waters to drink. So, and I mentioned the other one to him, that as the emergence of generative AI and also the robot, in the future, we envision in the future, in every home, you're going to have a robot with intelligence, and you have to teach your robot by yourself. So that means that now we teach our kids in our home, but in the future, you have to teach your robots. The robots from different homes will be different, with different abilities. So in the future, I think the science and technology will play a very important role for next 1 decade 2 decades and 3 decades to come. And Italy, maybe Professor Yaghi, you not know a lot of background information about Italy. The Industrial Research Institute, Technology Research Institute in Taiwan was founded 51 years ago. And actually our mission is to promote the industrial development through the technology innovations. In the past, actually, in particular for the semiconductor industries, we transform the technology into real applications, and actually a lot of companies come out, especially in the semiconductor industry, like TSMC and the UMC and Acers. So this is a very important mission for Italy to fulfill. And also, as President Lin mentioned about the typhoon, actually for the climate changes, really matters for not only for Taiwan, but also for the whole world. And it's about the time for Italy to play some role. So with your inventions, the new materials and all the new methods, I think in the future, Italy will find some chance to cooperate with your team and work in this way. And we're trying to have some solutions coming out to save our environment, especially for the waters. So that is later, you visit Italy, and we have a lot of what we have now to show you, and we're trying to find some opportunities to work with you in the futures. And finally, thank you for inviting me to here. And I wish for the future so we can work together to make the world an even better world, and also the environment we can keep the environment much greener. Thank you. Yeah.
Thank you, Dr. Wu. Now, President Lin will present a souvenir to Dr. Yaghi. May I invite President Lin and Dr. Yaghi to come on stage? The souvenir is the teddy bear of National Yangmingshan University, the 2024 version. Congratulations. And please return to your seats. Now we will be taking a group photo. The photographer will take the picture from the stage. So everyone, please remain in your seats. Please turn to the stage and smile. Another one. Ready? Okay. Thank you. Great pictures. So the forum will start shortly. If you have any questions during the forum, please submit them via the Slido link shown on the screen. Now, let's invite the moderator of today's forum, Dr. Albert Yang, Director of the Institute of Environmental Engineering, to give his opening remarks and introduce the 2024 10 Prize Laureate in Sustainable Development. Welcome, Dr. Yang.
Good afternoon, distinguished guests, ladies and gentlemen. Once again, welcome to NYCU to attend the 2024 10 Prize Masters Forum in Sustainable Development. As our president has mentioned, the typhoon is coming. So I hope everybody understands the risk of climate change is genuine, and we have to do something to make us sustainable. I mean, the human being. Judging from today's audience, in engineering terms, I think it has been proven that the pulling force of the Yaghi storm is stronger than the pushing force of Typhoon Cameron. As a faculty member of NYCU and an alumnus of UC Berkeley, I am honored and pleased to introduce the 2024 Tang Laureate in Sustainability Development, Professor Omar Yaghi. Professor Yaghi is currently the James and J. Chair Professor of Chemistry at Berkeley and a senior faculty scientist at Lawrence Berkeley National Lab. He is also the founding director of the Berkeley Global Science Institute. He is an elected member of U.S. National Academy of Sciences and the German National Academy of Sciences, Leopoldina. It may be worth mentioning that eight chemistry department faculty members at UC Berkeley have received a Nobel Prize. However, one has left for Princeton and the other one has left for Stanford, as well as another 10 alumni have got the Nobel Prize. Of particular interest to Taiwanese, Professor Yun-T Lee, Li Yuanjie 教授, an alumnus and faculty member at UC Berkeley, received the Nobel Prize in Chemistry in 1986. If you do not know, Professor Lee is from Hsinchu and now still living in Hsinchu, and his younger brother is teaching at NYCU in applied chemistry. Professor Yaghi has won numerous awards, for example, including the Tang Prize. He has already won 3 prestigious awards in 2024. If I try to recite all his awards, there is probably no more time left for his lecture. However, I would like to mention one particular one, the Rolf Prize in Chemistry and Medicine that he won in 2018. This is in close relationship to the Tang Prize in Sustainable Development. The Wolf Prize is awarded to outstanding scientists and artists for achievement in the interest of mankind and friendly relationship among people. The prize is awarded irrespective of nationality, race, color, religion, sex, and political views. Professor Jennifer Doudna, according to Professor Yaghi, again at Berkeley, won the Nobel Prize and the Rolf Prize in the same year. So I'm expecting Professor Yaghi is on his way to this very distinguished award in the future after the Tang Prize. And about the Rolf Prize, of particular interest, I would like to mention to Taiwanese. Professor Jianshong Wu, Wu Jianshong 教授, was the first Rolf Prize in physics in 1978, 10 years before Stephen Hawking. And quite a coincidence, Professor Wu is also a graduate of UC Berkeley, under the supervision of Professor Ernest Lawrence. Now we all know the Lawrence Berkeley National Lab and the Lawrence Hall of Science. They are all named after Professor Lawrence. The Tang Prize in Sustainable Development recognizes those who have made extraordinary contributions to the sustainable development of human societies, especially through groundbreaking innovations in science and technology. I cannot think of a better example than Professor Yaghi to fit this description. So without further ado, I would like to present you the 2024 Tang Prize Laureate in Sustainable Development, Professor Omar Yaghi of UC Berkeley and the Lawrence Berkeley National Laboratory. Professor Yaghi.
Thank you very much for that warm welcome and your kind words. I feel during this trip, I've been here now for about a week, I feel tremendous warmth from the Taiwanese people, from colleagues, everyone I met. Thank you very much for your hospitality. Thank you very much for making me feel at home. I'm looking forward to further cooperation with Taiwanese in every sector, academia and industry. And I think if you haven't heard my laureate lecture, you will see that we are naturally moving from the molecule to the material, to engineering the material into a device. And I hope that this also will be manufactured in Taiwan. And I will talk about this shortly, about what kind of materials these will be. So today, I'm going to present something about organic chemistry and how we extended organic chemistry into the infinite regime, the two-dimensional, three-dimensional regime, and how that has led to making viable materials for CO2 capture from air and CO2 capture from power plants. I will also present our results on molecular weaving, how to make molecular fabrics and why would you want to do that. Okay, so in the meantime, I will show results also about water harvesting from MOFs, from metal organic frameworks. Let me just say that we have invented a new kind of chemistry. And this chemistry signature is that we can take molecular building blocks, stitch them together into frameworks. And these frameworks are crystalline, which means that their structure is periodic throughout the material. So if you're using it for capturing CO2, it will behave exactly the same way and give you very precise properties. So crystallinity is very important for achieving the properties, precise properties of the material. The result of reticular chemistry has been MOFs, metal organic frameworks, and COFs, which are frameworks that don't have any metal in them. They're entirely composed from light elements in the periodic table. And I will also share with you how we can make weaving structures on the molecular level for the first time. So these chemistries have been based on the strong bond. We're linking the molecules by strong bonds so that we can make robust materials that can stay in the power plant for many, many years, doing many cycles. Or the MOFs can be used in a device to harvest water for many years. I will show you these shortly. But back in 1995, we showed that these can be crystallized. They can actually form in a simple way by mixing organic and inorganic. The yellow ball here indicates the space within which one can compact gases: hydrogen, methane, CO2, water, many things. And in 1998, we showed that when the pores are evacuated, the structures do not collapse. So they are architecturally robust. And in 1999, we showed that they have extremely high porosity, so high that 1 gram of material has the surface area of an entire football field. And that's because the inside of the material has much higher surface area than the outside. So if it's in a gas tank of an automobile, the automobile gas tank doesn't have to be very large because you can compress gases in small amount of space. The COFs we invented in 2005, and they have revolutionized organic chemistry. And I will discuss that more. So my story starts here. This is every student of chemistry in high school, they learn the Lewis dot structure. And that originated with G.N. Lewis, who used to be professor at UC Berkeley in the chemistry department. He used to be the dean of the College of Chemistry. He received the citation for chemical breakthroughs. This is one of the most prestigious awards in the world for chemists. And it's bestowed by the ACS. And it was given for this paper that he published in 1916. That paper described how atoms could be linked together to make molecules. And he didn't call them covalent bonds at the time, but he described what later became the covalent bond, what later people refer to as the covalent bond. That was the real beginning of chemistry, because now you can take atoms in a designed fashion and make molecules. And what I want to show you today is that we can go from the atom to the molecule and to the covalent organic framework. So why is this important? It's important because, so I've written the structures in Lewis dot structures, just like a high school student would. And you can see here, these atoms are going to the molecule is going to the framework. And what I want to say is that the molecule to the atom is what the framework is to the molecule. And what I mean by that is that the molecule fixes the position of the atom in a certain connectivity, geometry, and spatial arrangement. That's why the molecule is so useful. And the framework fixes the molecule in a very specific connectivity, geometry, and spatial arrangement. Except the framework encompasses space within which you can carry out new chemistry in confined space or compact gases. And when you are able to, as we have done, to functionalize the interior, now the pores could be chemically functionalized with precision to target very specific properties. And that's why COFs, as I'll show shortly, are extremely effective at capturing CO2 from air and from flue gas. But let me, just for the younger crowd here, let me just say that this field was completely absent. There was nothing, as Roald Hoffman here says, in 2 or 3 dimension, organic chemistry basically was a synthetic wasteland. There was absolutely no crystalline extended structures in 2D and 3D. So what we have done with COFs is that we have propelled organic chemistry into infinite 2D and 3D regime. And that's why COFs are now another very large class of materials, not as large as MOFs yet, but they will be because of their usefulness. Now, why was this chemistry not developed? Why did it take all these years until we came along in 2005 to develop this chemistry? Because when you ask a student to link organic molecules together, they get this. This is an X-ray powder diffraction. And everybody that has worked with X-ray will look at this and say, my God, this is junk, right? It's an amorphous solid. And I'm a chemist. And trying to capture CO2 from air, water from air, you need a very well-defined material that you can vary on the atomic and molecular level. You can precisely design. And for that, you need a crystalline material. It took an undergraduate, by the way, to open up this area in my lab. Undergraduates take more risk than graduate students. Okay? Because they're there for fun. The graduate students are all stressed out about their writing a paper and graduating and getting a job, while the undergrads are in there for the experience and the fun. This was Annabel Benin. Annabel took this molecule, and we anticipated that if she does this dehydration properly, then she will form this BOB linkage, and thereby making the very first 2D COFs, covalent organic frameworks. But the challenge is, can she make this crystalline? Well, she came into my office after trying for a few months, and she said, Professor, I can see in the X-ray powder diffraction a very tiny peak at high D spacing. And of course, that's exciting because order is beginning to show up in the product. And I said, okay, well, you go away and turn the whole X-ray powder diffraction just like an NMR spectrum with sharp lines so that you make a crystalline material. Well, she came back after a couple of weeks and said, I noticed that the crystallinity of the material depends on how long the tube is. We run these reactions initially in sealed tubes. And for some reason, she said that depending on the length of the tube, the crystallinity was variable. And I thought, well, that's really wacky. But it turns out, of course, it's not wacky. When you think about it, your byproduct is water. And water is hovering above the liquid, pressurizing this reaction to be reversible. Reversibility is what you need to make crystals. So as soon as we figured that out, it was these conditions that gave us highly crystalline material, and thus was the beginning of COF chemistry. So instead of that hump, her X-ray powder diffraction looked like this. Okay? And in so doing, we defied all expectations. People said these couldn't be crystallized, right? People did not want to approach this area. In fact, I interviewed at UC Berkeley, and I did not get the job because nobody believed that it could be done. And so I went to Arizona State University, and that's where we developed this chemistry. So here's a structure. It's a slipped graphitic structure with pores. And based on those reaction conditions, it turns out that with slight variation, you can not only crystallize boroxine-linked organics, but boronate ester-linked organics, triazines, imines, hydrozones, borazines, phenazines, amides, oxazole, everything an organic chemist works with, we can crystallize. And not only crystallize, but even after you form the structure, you can do all kinds of organic reactions on it. A dream come true. You have extended structures that are crystalline, and they can be modified pre-synthetically and post-synthetically, and still maintain the crystallinity, still maintain their high porosity. We can also make single crystals of these, just like organic chemists make molecules single crystals. Again, unheard of, unexpected, and completely goes against what people have been doing. And here, you use these anilines to slow down the imine reaction, and thereby you can get crystals. Okay? These beautiful crystals of an extended three-dimensional COF, and all of these are three-dimensional COFs. Very beautiful crystals that are amenable to house or laboratory X-ray diffraction. So COFs now are being investigated in, I don't know, maybe 100 different groups around the world. It's a field that is growing. So that's basically was the opening. Now, this is an impossible structure to crystallize. I didn't even think we could crystallize this because this structure is made entirely from carbon-carbon bonds and carbon-nitrogen bonds, some of the strongest bonds in chemistry. And the state of affairs is that everybody believed you can crystallize it, including myself. But it made me believe that everything can be crystallized, provided you find the right conditions. And these are the conditions under which this structure crystallizes. Why am I so excited about this result? Because structures like this are going to save the world. Why? Because this backbone is stable in 12 molar HCl in acid, strong base, KOH, and even corrosive materials like N-butyllithium or methyllithium. This is the ideal materials to stay in a power plant or in a device capturing CO2 from air, or from a power plant preventing CO2 from going to the air. And indeed, this student functionalize the interior of that MOF with amines covalently bound to the backbone. And then we did a lot of studies on this. I'm just giving you one slide to show you the results. I was told to speak only for 30 minutes. So this is the CO2 concentration in Berkeley air. Okay, it varies around between 400 to 450 ppm. This is the relative humidity in Berkeley during the course of the experiment. Okay, it goes up and down. And this is the CO2 uptake. And it scales with whether you have higher humidity or lower humidity. But the material has beautiful behavior at the same, if you take a point here at this humidity and in the same humidity over here, there is absolutely no loss in performance. And the capacity of the material for taking CO2 out of the air is 1.5 millimole of CO2 per gram. You only need 1 millimole of CO2 per gram, and the material should be cycled 100,000 cycles to have a commercializable material. Well, we're already over the minimum requirement. And for flue gas, it's even better. Flue gas based on burning methane or based on coal, we do much better. Okay, there is no other material that has this behavior. All installations now for carbon capture are either using amine solutions, which are energy intensive, corrosive, and create their own environmental problems, or they use solids, but these solids are not stable long-term under cycling conditions. This one is. Why? Because chemistry produced a backbone that is based on carbon-carbon bonds, the strongest bonds in chemistry, and I showed you the stability, the chemical stability. That's the sort of resiliency you need in these materials so that they can carry out hundreds of thousands of cycles over many, many years without having to replenish the material or replace it. So I would say the scientific challenge of capturing CO2 from air is solved. What remains is for Taiwanese to scale up this material. It's the only country, I think, that has the boldness to really do this, to scale it up and manufacture the COF. BASF is very successful at manufacturing MOFs, but they are not manufacturing COFs. So I think that this is an opportunity for collaboration. Now, I like this application because, in fact, all the hardware is already built. It has materials in it, but the materials are inferior. So if you scale this up, it goes in those already developed hardware. Okay? So I think that this is, I like to say that right now in my lab, recent results show that we can double the uptake because we figured out the chemistry inside the pore. We figured out what is water doing versus CO2, and we can double this uptake. Okay, so I'm very happy about this result. It's very clear that we have made a breakthrough in terms of CO2 capture. Now, for water harvesting uses MOFs. And this particular MOF is very stable in water. Okay, this is made from aluminum pyrazolate. Okay, and this is a crystal structure, and what I'm going to do is I'm going to take one pore out and slice it and show you where each water molecule goes. This is all evidence from X-ray diffraction. We figured out exactly where each water molecule goes. Now, you'll see that the first 4 water molecules go to the hydrophilic region. The hydrophilic regions are separated by hydrophobic regions. When the hydrophilic regions are filled with water, they bridge over the hydrophobic region. This push-pull of water in the pore allows you to modulate and have binding energy sufficient that requires low regeneration temperature. Okay, so let me show you how this MOF operates. So that's the one pore. We're going to slice it. and water is going to go to the hydrophilic region. Okay, 3, 4 water molecules, and now more water is attracted through hydrogen bonding to the hydrophilic region over the hydrophobic region, and the pores get filled with water. This moth takes up water at 5% relative humidity and at all humidity levels above that. If it works at 5%, it works at 10%, it works in Taiwan at 85%, okay? So this moth can harvest water anywhere in the world at any time of the year. And so it's an important moth. We've scaled it up to hundreds of kilos. BASF is gearing up to scale it up to multi-ton quantities. In the meantime, we wanted to take this outside the lab and show that in fact it works in the desert or it works in devices. So we designed devices like this one, the size of a microwave oven, that deploys 200 grams of water. There's a door there where air goes in. The moth takes the water out of the air, and when the moth is saturated, it gets heated up, and water comes out of the pores and condenses, and you'll see a puddle of water in here where the water is collected. From 200 grams of water, of moth, you have 5 liters of water. That's basically an appliance that could sit in your kitchen, giving you ultra clean water every day for 6 to 7 years. Okay, and what is the cost of 200 grams of an aluminum moth? Aluminum is one of the cheapest metals. Okay, so it's a cheap material that is sitting there harvesting water from air and giving you clean water that you're in control of. Okay, you know its purity, and you can adjust its taste the way you like. You can mineralize it, make it tasty, you can make it carbonated. You can make it sweet if you want. And it's ultra clean.
Ready, 2, 3, action. Cheers.
Okay, it's nice because he harvested this water himself in Arizona. Okay, so his experiment succeeded, he's excited. So he drank the water because the water is ultra clean. The taste is not very nice because it's distilled water. So, but if you mineralize it, it'll be very tasty. To him, it was sweet because his experiment succeeded. This is a beautiful illustration that you can create water from air. We have created a new source of water. And that's powerful. That's going to change the water equation. Here's another device. I'm just going to show you that we're beginning to scale this up. And this is, I call it rain in a box, okay? This is fans pushing air inside the moth, and then the moth gets heated, and then droplets come out, okay? This is another one. Okay? It works. It also works in Death Valley. The students made a briefcase-size device that works even without electricity. It can take up water from the driest deserts, you see there, in Death Valley. Okay, with no energy input aside from sunlight. Okay, no, there's no solar panel, just ambient sunlight. The device, the interior of the device gets heated up, water comes out of the moth and gets condensed. Now we are at a stage where we have a size, about a size of a small refrigerator, and this device delivers 22 liters per day. Okay, and so where are we today? We are at a place where 1 ton of moth without electricity will give you 3,000 liters a day. When it's electrified, it'll give you 60,000 liters a day. 1 ton. 1 ton is probably the size of this podium. Sitting there, harvesting water every day for 6 to 7 years, 60,000 liters a day. And our estimates is that at about 1 cent per liter, just as a starting point, 1 cent per liter. So I think this is now ready to be handed over to somebody in Taiwan to manufacture, to modify and make it more robust as a device. But all the chemistry works, the harvesting works, the cycling works. Okay? So I can't do that in a university. Okay, so I want to finish by just doing something for fun. Okay, I want to just impress upon you how much control we have over materials. And this is what you just saw is only the beginning. Weaving is the oldest way of making anything. And basically it's interlacing of threads. And it's the same, the old weaving and today's weaving is exactly the same, except we do it now faster and more sophisticated. It exists in biology, I'll skip over that. The idea is, could I produce this on the molecular level? How could I take a string of molecules and weave them in and out another string of molecules? And this problem is solved by reticular chemistry. Why? Because we think in terms of building units. The building unit of a structure like this is just this crossing. If I can make a molecule that's this crossing and I control the angle between the crossings, then I can just assemble them the way I assemble all other materials. The result would be woven structure, but not one where I have taken a thread and woven, but rather made it through the building block approach. And that's exactly what this student did. She took a mutually embracing complex like this with copper bringing 2 phenanthroline units, functionalized the molecule by 4 aldehydes and copolymerize it with an amine, and there it is. You make imine, and we know how to crystallize the imines. It doesn't know that it's woven, but it is. And the metals make the structure periodic, it's crystalline. Now, if you don't want the metals there, take them out. By adding KCN, you take them out. And if you want them back in, you can add it. And you go from a crystal to a non-crystalline material. Because this is like a fiber, like a cloth. X-ray powder diffraction of the metallated, the demettallated, and the remettallated. That means the structure, when you take the metal out, does not get unzipped because it is woven. It's crystalline. And okay, so we can make that. And we also know that when a large molecule approaches the pores and the pores are not large enough, the structure expands to accommodate a guest. Everything you can think of, all structures you can think of, extended structure, could be woven. Okay, why am I so interested in weaving? Because look how resilient my shirt, my jacket is. I can bend it 1,000 times, nothing happens. Why? Because it's woven. Because the stress I am putting on the material is not going to the covalent bonds, it's getting absorbed by, the energy is getting absorbed by virtue of moving the threads with respect to each other rather than stressing covalent bonds, which is normally how materials break down. That's why weaving is so great. Well, you can weave anything you want. So let me show you how we weave this one. Okay, looks impossible, right? We can do it. Here it is. This is the building unit. And if you further decompose the building unit into its building units, you see that this is the molecule I want, and I want to copolymerize it with this kind of molecule. A triangle with this mutually embraced. Well, we already know what that is. This is the mutually embracing, this is a triangle. And it begins to be woven. That's it. Highly crystalline, and here's a structure. Okay? That's all entangled, covalent building units that are entangled like chain mail. It's a three-dimensional chain mail. This is just one unit with its immediate surroundings. Okay, let me finish by showing you that this is extendable to any structure you can think of. Here is this. Okay, try to do that in chemistry by having threads, and this is chicken wire. The way you do that is you take a molecule that is like a helicate and you copolymerize it with another molecule and you make it. Okay? This is it. That's the molecule. It's a two-turn helix, and this is a strut that links these helicates together. Okay? I don't need to weave. I don't need to do what that machine is doing, but I can use reticular chemistry for that. So this is what reticular chemistry does. It takes the building units, puts them together to make incredible materials, in this case, woven. Here's another one. This is chain-linked fence, okay? Slightly different than chicken wire. And this is how we do that. Okay. This is all the X-ray diffraction and electron diffraction. How about chains?
Steel cutters now make notches on both sides of the wire. These notches mark the place where the wire is to be sliced into link-sized pieces. A mechanized knife makes the final cut at the notches. Next, roller arms loop a cut piece of wire around a steel finger.
Okay.
The roller arms make it look easy.
Try to do that.
Exerting tons of pressure in order to shape.
Try to do that in chemistry. You can't, but you can use it with reticular chemistry. I'm very happy to say that we have succeeded in making that kind of chain. Now we can weave and we can knit on the molecular level. Why am I so excited about this? Because for the same reason that these are resilient, when we add to polymers, construction polymers, or things like, in this case, polyimide, when we add small amount of these woven structures, we can increase their hardness and toughness. Usually additives will increase hardness, but material becomes more brittle. But in this case, they become tougher and harder and tougher, so they're more resilient. And in my final slide, I want to show you a demonstration. This is polyimide without weaving. This is polyimide with weaving, 1%, 3%, and 5%. And I'm stretching, I'm pulling them apart to see how tough they are, okay? So this is the polyimide. They're all being pulled apart at the same time. You see the polyimide break first, and then after a while, you see the 1%. Okay, for materials, that's huge. That's a huge resiliency as a result of adding 1% weaving. So at the end of all this, what I want to say is that we have recently, my whole lab has been converted to using AI, generative AI and LLMs, to make the discovery of these materials much faster than what it has taken me, 35 years to get here. We want to make things faster, and we already have what I call the digital discovery cycle working to make better materials for CO2 capture, better materials for water harvesting, and other applications. As you can imagine, muffs and coughs have many, many different applications. So finally, I want to acknowledge my students and the funding agencies, and I want to thank you very much for the honor of being here and for the Tang Prize. Thank you so much.
Thank you, Professor Yaghi, for such an inspiring presentation, bringing such an exciting research work. Now, it's time for the panel session. Let's welcome today's moderator, Dr. Yang, and our panelists, President of Academia Sinica, Dr. Liao Junzhi, Academician of Academia Sinica, Dr. Wang Yu, and Senior Vice President of Industrial Technology Research Institute, Dr. Li Zhongming. For the audience, please remember to scan the QR code to submit your questions online via Slido if you have any questions. Dr. Yang, the forum is yours.
I would like to start today's forum by asking our experts on the panel to share their experience and insight for about 5 minutes each in the subject matter before I open the floor to the questions and answers. So if you have any burning questions, you can submit them through the Slido. So let us start the short discussion, starting with Dr. Liao.
Okay, thank you. First, congratulate to Omar, who is my former colleague at UCLA and a good friend. We have seen each other for a long time. We were in the DOE center together when we worked at UCLA. And every time I heard him talk was something completely different. And throughout the years, he started from MOFs to COFs. And I visited his lab a year ago in Berkeley. And now it's something different again. So it was truly amazing how fast he can move the field in a completely different direction and also with completely different way of thinking. So this is what Omar is about. And we all admire his enthusiasm in science, but most importantly, his enthusiasm in training students. Okay, many of you probably don't know that he has been involved in setting up global academies, what do you call global centers, in training the graduate students in different countries. And he has a passion to train graduate students, as you can see in his talks. And today, he gave a wonderful talks, and I think it's very inspiring to our students and young faculty or old faculty even. He started from something very fundamental, ask the question, how can we assemble molecules together? At the end of the day, he found that this is not just for the sake of curiosity. It may save the whole world in many different areas. So now raise the question, what is more important? We start something from curiosity or start something from a target mission or somewhere in between? So we may hear what Omar has to say, how to balance this, or maybe it is not important to think about your goal in the beginning and just focus on what you are interested in. And then I remember about a year ago when we talked at Berkeley, that was a time when generative AI was just started. And we had a discussion that you were not very confident or optimistic that AI could help in the exploratory research that you are doing. But now it seems like at the end of your talk, you had different thought. So I'd like to hear you comment about that. That'll be very interesting. So it is truly important that we recognize that this is a new area. And as Omar said, the next step is to realize his invention in manufacturing. And Taiwan, many people know that manufacturing is in our DNA. So particularly while in Hsinchu, this town is full of manufacturers, innovative manufacturers. We can manufacture anything better than anybody in the world. Okay? So I also like to see what Omar thinks about the challenge in realizing these COFs, MOFs, or even the weaving materials into something that's useful, that's marketable, that can save the world. So these are a few questions that come to my mind. I'm sure many of you may have very insightful questions, and we'd like you to raise those questions and encourage you to take this opportunity to discuss with Dr. Yaghi. Thank you very much.
Thanks, Dr. Liu. I think Omar has jotted down all the questions. So let us pass on to Dr. Wang first for his 5-minute remark.
First of all, congratulations again for Yaghi getting 2024 Tang Prize in Sustainable Development. We all understand or aware of the sustainable development. We're talking about all the time. But I guess we're not doing enough. And Professor Yaghi just showed us or demonstrate that everyone, as a scientist, can contribute into this field a lot and change the world in a few years' time. As a chemist, we were often blamed of pollutions. We are polluters. And I often argue with people that this is because of the petrochemistry. But chemistry includes everything. And we chemists like to say that chemistry is the central science. I also was attracted by the beauty of the molecules, crystals, and finally the materials. And so I followed the steps. Although I was graduated in the same graduate school in Illinois, but 15 years before Yaghi did. But as Moth, and I didn't know him in person, but I didn't know his work a long time ago. And I said, wow, this Yaghi has produced so many moths and coughs. And that was started in 90s. I noticed before that, in chemistry, organometallic is a big field. And since 90s. And as a chemistry and crystallographer, and I do really appreciate what we can do in the sustainable development. As I said, we're aware of the problem that although we were blamed as a polluter, as a CO2 producer, etc., and here we finally get some ways, and efficient ways of taking this pollution out of our air. But to achieve the goal of having sustainable world in the future, and we need not only the scientists work together, but also we need everybody to implement the concept that we all have responsibility. We all should pay some responsibility towards the sustainable development. And now we have all the science and technology developed by this expert, and but the rest we need the worldwide effort, not only a few, but worldwide scientists and human beings to work together, and synergetically, then we can have hope to achieve and the time is not in our sight. And we start this late, but I hope we can all play some role toward this sustainable development. And thank you.
Now comes to Dr. Lee for your remarks.
Congratulate Dr. Yaghi, and also I'm very appreciated and also impressed about today's presentation. And also as I remember that we are familiar with the MAF even 20 years before or 30 years before, because in ITRI, we are always working on this for tried many applications based on MAF or COF, but today I also very impressed that we heard about the weaving structure. This is also a very interesting structure because as a polymer researcher like me, I'm also working on the polymers for a very long time, and working on the hybrid structures and the heterogeneous structures. And usually, as polymers researchers, sometimes we are talking about IPN structure, interpenetrating structures. However, today, Dr. Yaghi provides a very ideal structures manufacturing process. Not only just idea, also he also point out a very clear how to make the heterogeneous like weaving, like clothes, knitting process, and with a very easy way and a clear way. So this will provide a very good, maybe in the future, for some biomedicals, like proteins, biomaterials preparation. Actually, proteins also biomaterials and biopolymers. And so I'm thinking that this will be a very good. And also I'm interested about two topics. One is his research works. One is about the COF, because we are also working on the carbon dioxide in these past 6 years or 7 years, because we have a very severe issues. We burn a lot of fuel to produce the electricities and the powers for our industry. And then at the same time, we have a lot of carbon dioxide emissions. So this time, COF materials may be as very good candidates for us to use it as carbon dioxide absorbers, and also provide a very good approach for us, because currently we are using conventional absorbents like ethanolamine complex and like that, and also some of the process we are developing. However, if we can combine with the COF, I think that this is also another opportunity we can co-create with Dr. Yaghi, because also I'm appreciate that he provide this opportunity for us. And during today's, I'm very excited because he said that he is also opening the window to co-work with Taiwan. And so as researchers in ITRI, we are expecting this. And also for MAF, because we are also have a group working on the water treatments, and also a lot of the water issues also in Taiwan. Today we have a coming typhoon, and usually we are expecting typhoon, but we don't expecting the damage, and we expecting typhoon for waters. However, if there is no typhoon, there will be no waters for Taiwan. So I think that the solution approach from the MAF to create waters, I think this is a very good approach. And also I'm also very interested that I already heard from Yaghi today's presentation that they already have some device. So in the beginning, he said that from molecular to materials and also the final device, he has already proved and get the roles on the roles. So I think that today we can learn more from Dr. Yaghi, and also we are expecting that we can co-working with him in the future, and also create a real device or systems based on Dr. Yaghi's new innovation molecule. Thank you.
I guess this is always the advantage of being sitting on the panel, because you had the chance to ask the first set of questions. I think now may be a good time for Professor Yaghi to try to respond to some of the questions from the panelists.
Yeah, thanks everybody for your warm words and congratulations. I want to address the first question that my colleague Jim has brought up, the question of curiosity-driven research versus directed research. And I can only state the facts, and then you do with them what you like. The fact is that when I started trying to develop particular chemistry, I was really just interested in the beauty of molecules. I would say, really, I was doing curiosity-driven research. That's not to say that I was clueless about how important it would be if we succeeded in building structures through the molecular building block approach. I knew that that will be a new way of making materials, and potentially it would have many applications. But quite honestly, I did not set out to solve society's problem or to capture CO2 from it. I did not. It was really a curiosity-driven research. But as smart people, when you invent something, you have to ask, well, what is it good for? How can I use it to serve society? We have that obligation because society pays for that research. So that's how reticular chemistry was developed. Now, I would like to say that indeed, when Jim came to visit me, potentially 2 years ago? A year ago. I was beginning to be, I was doubtful that AI could help. Because I always thought, well, chemical intuition will always win out. AI is not going to give you that novel approach or novel material. Well, we started experimenting with LLMs. I had a student just start using conversational language, ask the ChatGPT to do things like text mining or image mining or predicting how to make a MOF. And we were really successful. I mean, we published about 10 papers on this already. We were very successful in doing research faster than the human. And it made me wonder, why is that? Okay, is the human not as smart as the LLM? Are we not as creative? Well, it turns out that we researchers, we approach our experiment and we decide what experiment to try based on the chemical intuition or what is happening in our field that other people say is important, and on what our colleagues and advisors tell us should be done. Like I advise my students based on my own biases, and some of the students are advised by senior students based on the senior students' biases. All experimentalists know the pitfalls of that. And I realize that we're all advising things that are not based on sound science. They were based on chemical intuition, which is wrong, because it's not based on 100% facts. Okay, for example, a student that comes to you and they say, oh, my experiment didn't work. And you say, well, why do you think it didn't work? They very readily will list 10 reasons why it didn't work. And if you go through each of those reasons with them to try to find out, is that based on sound science? And the answer is almost always no, 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 no. And then immediately I realized that I have a problem, that we chemists have a problem in our research. If an LLM can do better than my researcher, I have a problem. And the problem was that we are making decisions not based on 100% sound science and facts. And when an LLM does the text mining with 95% accuracy, and now it can give me a table of all those facts, and I can make the decision based on those collected facts. Now I am doing better as a researcher. So that means that the LLM can be a collaborator with my students, with me, with our researchers, to make things, to make the decision of doing an experiment or pursuing an observation based on sound science rather than chemical intuition. That's just one outcome of using the LLMs. Another outcome is that not of the LLMs, but the generative AI, I call it the digital discovery cycle, where you use robotics, image recognition, build data sets, and modify your machine learning algorithm. This cycle, I find that even at this preliminary stage, is doing 20% better than our researchers. Why? Because it's exploring the much larger space that exists in that class of materials than my students. My students are restricting themselves to what has been done in our group, the conditions under which we are using. But the space is much larger, and that can be explored through robotics and the digital discovery cycle. So I am completely converted, and in fact, since I met Jim, I have converted all my group to an AI-driven research. 20 people. You cannot join my group unless you're interested in blending AI with chemistry research. And it's been really fun thus far. We're learning new things. So I think I'll stop here so that I don't consume all the time. But I will answer some of the other points as we discuss.
I think for sustainable development, the next big challenges that facing mankind is the energy problem. And I have a few questions related to each other. Is about if we can capture hydrogen, full MOF or COF, that may be a great energy source. So the question now is, what is your opinion on MOF or COF in order for you to design for hydrogen storage application? And then at the same time, after you capture them, when you want to release it, how do you make the control? Because the hydrogen is explosive.
So hydrogen storage, so far you could use metal alloys to bind covalently hydrogen, make hydrides, and use the alloys as a storage medium, and then you need to heat the alloy to high temperature to release the hydrogen. It's not ideal. The alloy becomes brittle, and some of the other systems other than alloy, like chemical systems, liquid or molecules that react with hydrogen, sometimes are not reversible. So each class of materials that has been used for hydrogen is not ideal. MOFs, COFs, because hydrogen is bound to their pores through physisorption rather than chemical bonds, it's thought to be ideal. The problem is the interaction is weaker than you want it to be. We started out with that interaction being about 3.5 kilojoules per mole, and increased it by modifying the pores up to 12 kilojoules per mole. But we need to get to 20 kilojoules per mole. It needs to bind as strong as a hydrogen bond. Are we going to get there? I don't know. Nobody is funding hydrogen in various governments around the world. There isn't a big push to fund hydrogen at the level that the problem needs. This is a difficult problem. And we need funding to solve that problem. Okay? So I get a little bit of money from industry to work on hydrogen, but it's not, I have to admit, it's not as intensely being worked on in my lab as CO2 or water, because that's where I get a lot of money to do research. So, but I'm interested in the hydrogen because hydrogen is the best or an ideal fuel. And I think that ultimately we have to deploy hydrogen on a large scale. So maybe Jim has different ideas, I don't know, but I think that hydrogen, I think we should have invested tons of money on hydrogen instead of the electric car. I think electric car is a diversion, and it's a marketing gimmick, and it's not solving the energy problem, it's not solving the pollution problem, okay? So we should have turned some of that money, or maybe all that money. For example, we, with BASF, developed a methane car. No change in the petroleum-based car, in the gasoline engine, in the gasoline tank, other than stuff the tank with MOF, and your tank will hold 3 times the amount of natural gas, methane, as a tank that doesn't have the MOF. Much more than a tank that doesn't have MOF. 3 times. And you can drive for 500 miles without having to refuel. But because of the electric car and the hype around electric car, all the contracts that we had to produce that car dissolved. Everybody wanted to do electric because there was a marketing campaign that electric is good. But the car is there, and it would cut our pollution by 50% overnight. The CO2 emission will be cut by 50% overnight. We're not doing that right now, because natural gas burns a lot cleaner than petroleum, doesn't have contaminants like mercury and other things. So, yeah, if I was a billionaire, I would be going for the methane car.
You become another Elon Musk. Fund your own research. And here's a very chemical question from the audience. What's the mechanism, chemistry, behind the gas molecule capture? Is there any intermolecular interaction between the pores and the molecule themselves?
For hydrogen, it's physisorptive forces, polarization forces that are holding the hydrogen into the MOF. And to release that, it's easy. You just release the pressure with slight heat, then it comes out. For methane, it's the same way. Physisorptive forces. Basically, the methane or hydrogen are attracted to the MOF a lot stronger than they're attracted to themselves. And so they assemble much closer to each other in the MOF than without the MOF. In the case of CO2, you're making a covalent bond between the amine inside the MOF, or the COF in this case, and the CO2. And that's a covalent bond that you have to break by heating. And with water around, it's easy to break that bond and evolve the CO2 after it has been included. In the case of water, it's just hydrogen bonds. Just hydrogen bonds are the bonds that are attaching the water to the framework. And those are easy to break by heating. Yeah.
So the interaction depends on the nature of the molecule.
It certainly does.
Here's a question that asking whether the MOF of the COF material, can it be dissolved in water or be fluidized so that it can be injected into the soil pore so that we can capture selected contaminant in the soil?
I like that. I was hoping that the question is, could you use MOF to release chemicals into the soil, like pesticides? Pesticides and right now are used as liquids to fumigate the soil in planting, crops. So the idea was that you make a MOF that can hold the pesticide molecule, and then when exposed to moisture in the soil, it will release it locally, rather than spew all those liquids everywhere and the liquids seeping inside in our water sources. So that's one application. I like the idea of, you could, and people have demonstrated, that you can use MOF solids to extract polychlorinated molecules from water. That's easy. Mm-hmm. But injecting a liquid that then assembles around a molecule is, it's an idea that I've had for a long time. I don't see how that can work with everything that's around. yeah, with all the other chemical species, ions and so on that are around, yeah.
Because that fall into my area of specialty. We always have problem nowadays. We have certain contaminant already in the soil. No matter you try to take it out or you want to get something in to absorb them, the problem is how can you get the material to the correct place where the contaminant is. So if the moth and the cork are in solid form, and you think about the soil pores is very small, how can we get this solid into the right place unless you can fluidize them so they can inject them, or by another driving force to drive them to that location?
Difficult problem.
Okay, let's move on to the next question. Actually, President Liao has mentioned, what are the challenges now in order to put this technology into the marketplace?
Well, MOFs are already in the marketplace. They've been commercialized for capturing CO2 from cement plants in Canada. And BASF a year ago had a press release saying that they are scaling up that particular MOF to 100 tons per plant, and it's capturing carbon dioxide from cement plants, and carbon dioxide is not going into the atmosphere. So the MOFs are already commercialized for that. I am, like I said, I think the challenge for us with CO2 from air is that we need to scale up the COF. I worked with BASF for many years, and it took us about 5 years to scale up MOFs perfectly, having an environmentally safe way of scaling up the MOF. I hope it doesn't take 5 years to scale up the COF. The nice thing about the COFs is that the components are not very different than the components of polymers, and it's based on organic chemistry. So I'm hoping that our organic chemists are skilled and the field is mature, that we can find ways of scaling these to multi-ton quantities. And once you have them scaled up, they're very easy then to shape them into different particles and put them in these devices that already exist. So that's where I think a partnership with a country like Taiwan would make a big difference. Yeah. The water harvesting, we're already at the prototype, which a manufacturer can take that prototype and optimize it. Okay, make it smaller, make it look nicer, whatever is necessary. But the prototype that we have already works, right? But it has wires sticking everywhere, and it needs to be industrially designed.
Following that question, where do you see the advantage of Taiwan when compared to other countries to commercialize these technologies?
My understanding and my observation is that Taiwan has a very strong, skilled workforce that is able to take a prototype like what I have and manufacture it, do the necessary steps. I call it the scaling cycle. Do the scaling cycle. Improve the prototype, industrially design the prototype, source it, pilot it, and manufacture it. I'm not going to do that in my lab, and a chemical company like BASF may not be able to do that. I think it needs very people or companies that work fast, right, and have done this before.
From that perspective, would our local specialists want to chip in?
I think that just follow the Dr. Professor Yaghi's opinions. I think that for Taiwan's industry, especially our chemical industry, we have a lot of potentials to focus on this area, especially for the carbon dioxide capturing and utilizations. Because maybe for the direct air captures of the carbon dioxide, maybe it's not so easy in Taiwan because our land area is not so much bigger compared with the USA or many other areas in the world. However, in Taiwan, we have a very complete petrochemical industry and also the specialty chemicals industry. So recently, we are also building up the carbon dioxide pilot scales, capturing system and the utilization systems. And also for Dr. Liao's group of academia, they also build up with pilots with Taiwan's power plants based on methane hydrogens. So we have a very good infrastructures for to promote or also to make it industrialize this technology. If we can, based on these MAF technologies, we are thinking that we already have some pilots. For example, we can capture the carbon dioxide 200 kilos per day. We have these kinds of pilot systems. And then if we change some of our catalyst systems from our current system to MAF systems, and also we have some capabilities to producing the MAF itself by our technologies based on if we have some of the opportunity to co-work with Professor Yaghi, then I think that there's a lot of potentials. And also, I think that this is the right time we can invite some of the Taiwan's local industry to join this, especially like Formosa industry or the Taiwan's CPC. They have a very good skilled engineer and also some of the researchers, and they can join with this. I think that based on this, I think Taiwan's flue gas is a lot of potentials because flue gas from power plant or from other burning process, and then we can use it based on more process, and we can capture this carbon dioxide and for following utilization. And this is one of the potential, and I'm expecting that this kind of successful application in our industry.
Here's a question from the audience. So we all understand there are many bacteria, virus that can cause health problems. And these bacteria, virus will exist in air and in water. Is there any way we can use morph also to capture this harmful bacteria or virus from the air and from the water?
That is a different size regime. We're working with molecules, small molecules that are causing havoc in the environment and sustainable, like hydrogen, CO2, methane. All these things are much smaller, much harder to deal with. I think that capturing viruses is already solved, right? So you just need filters of that micron regime or nano regime.
You need a mask.
Yeah, you need a mask, exactly. Yeah.
And Yaghi, an audience want to ask you a question, and he want you to have a crystal ball to look into what's the major breakthrough in the discovery and application of particular chemistry.
What is
the next major breakthrough in the discovery or applications of particular chemistry?
Well, I mean, if we can implement water and CO2, do you need anything else? I mean, there are a lot of other things, but this is already a handful. I would say there is an intersection that is emerging between materials, AI, and X. X being, we discussed today, climate. Or it could be biotechnology, or it could be some other application, electronics. So climate is great because AI times materials times climate is ideal. almost every major government in the world is investing in climate. And almost everybody believes that AI is going to help society do things better. And you have the materials. The materials are mature. MOFs, COFs are sufficiently mature as materials. MOFs are being scaled up to multi-ton quantities, and you have almost infinite number of variations that you can make with them, and COFs are not very far behind. So you've got these three things working together. This intersection is ideal. For the very first time in the history of chemistry, chemistry has climate to fund and make inventions. Before climate, it was drug molecules. Polymers, some people say that's engineering, not chemistry, but let's say polymers. The third one is really climate, and this is the right time. We have resources of governments and companies behind funding AI, materials, and climate. And so I think this is the right time. I think if anybody wants to be in this space, whether you have a startup or whether you are a student or a new faculty, you need to be in this space, AI, materials, climate.
I think I got this question from junior researcher or even students. Say, Professor Yaghi, you have enjoyed a very successful and fruitful research career. But then for those who are on the panel right now, that's the students talking about, when we entered academics, the world was not the same. Like myself, I've never been a postdoc before I become a professor. But this day now, the thing has changed so much now, especially those who are in science. They need the 1 postdoc, 2 postdoc, even 3 postdoc position to get a formal faculty positions. So what advice you would give to young researchers and graduate students now on how to pursue their academic career in research and teaching?
Well, everybody thinks that when they're looking for jobs, it's the worst time in their age, basically. Everybody thinks that their situation is the worst that it has ever been. And I think that things are getting better and better and better. When I interviewed for academic positions, there were only 5 positions in the whole United States. Today, when my students interview, they can interview for chemistry, materials, Chem-E, and maybe something with computation. Environmental engineering.
Civil engineering.
So when they're out in the market, they apply to about 60, 70 positions. So there are plenty of positions available. I would say that one of the problems is that when you go to graduate school, you need to understand that you need a skill set that is unique. And I just mentioned an area where your skill set would be unique and you would be highly sought after. I noticed that many students want to do a secure PhD, meaning they want to follow a blueprint that gets them to a project that works and a publication resulting from that project, and then they get a job and they're secure. Well, they're not as competitive as a graduate student that joins a group for the love of science and they want to break new grounds and they don't care whether there's a paper or not because deep down, paper will come, right? They don't take risk. And when you don't take risk, you're not going to develop your skill set, a unique skill set that everybody wants. Okay, so I think that at least those two distinctions would have very different prospects in the job market.
And I think this is another question from a young researcher. He says sometimes discovery is out of luck.
Pardon?
He said research discovery sometimes is pure luck. And then in your opinion, how do we mix systematic theoretical reasoning and bold trial and error in research?
nothing happens by luck. Okay, if we had another 3 hours, I will tell you about how each discovery was made in my lab. It was hard work, but it was, we chose a problem that everybody thought it's not gonna work. Who does that other than crazy people like me, right? You choose a problem, a challenging problem, and you work your tail off. Nothing is luck, okay? Luck attends those who are at the bench working, observing, and understanding the system. That's not luck, that's hard work, right? That's not luck. So there is nothing magical about doing great things. The magical thing is that you intend, you have the will to break new grounds. Well, that's high risk, okay? That's high risk. So do you want to take high risk and make great discoveries? Or do you want to just follow the trodden path? So that's not luck. What I would say is that you need a new idea, and the way to get a new idea, just look around and say, well, what doesn't work? What are people saying is impossible? And go after that problem. What doesn't work? And go and make it work. That's the easiest way of doing something unique. So I'm not sure what was the other part of the question. Did I answer it?
You do.
Yeah.
I think now it's time we come to the last question. There's also a very specific question.
Can I add on to Omar's answer? And I have to say that I agree 100% with Omar's comment. And that is exactly how I felt when I compare my career in US and in Taiwan. When I went to United States, I think myself worked pretty hard. But as a grad student, every time I go to lab, go to computer room, there's always people there. Okay, always people there. We think we Taiwanese work the hardest. No way. Okay, when we hired assistant professors, we think we work very hard. We are overworked, underpaid. If you think of the kind of people we hired, we triaged in selecting assistant professors. Almost everybody has the Omar Yaghi's quality in order to get a job. So that's a common criteria. Okay, of course, some are more successful, more imaginative than others. Okay, but nothing happens with luck. That's exactly what everybody should remember. And luck goes with those who work hard, okay, and think smart. Okay, at least you have to work hard.
Yes, I would like to also echo this topic. Just a little. I think that we need the hard work, and also we are expecting the serendipities. Because not only just not luck, it's a serendipity. Because we have serendipities, after a long hard work, we can have some breakthrough and also have some innovation. It's not just luck. Thank you.
I think it's time we are coming to the last question. Many are asking about the secret on what's the best way you can capture carbon dioxide from the air. And then later, how are you going to reuse those carbon you have already captured?
Well, first we need to capture it, because the longer it's in the atmosphere, the more storms are going to get more intense, like this hurricane that's hanging out south of Taiwan. So we need to capture it, and right now we don't have a good way of converting it. My colleague Jim Liao has a great way of converting it using biological means. I hope that this can be massively scalable. Then we can use that CO2 to convert it to high-value chemicals. So in the meantime, we're pumping it under the ground, mineralizing it under the ground, making it into carbonates and other things, or trapping it in large spaces under the ground. But this is a crisis. So you have to pull the CO2 out of the air. What I neglected to say about a comment made earlier, CO2 is a crisis, but we're not treating it like a crisis. We say, yes, we need to capture CO2 from air. We put money behind it, but we're not putting, when there is a crisis, we put billions and hundreds of billions of dollars for a country like the United States behind that crisis, whether it's the housing collapse or the pandemic or any other problem. We put billions of dollars, hundreds of billions of dollars. We're not putting hundreds of billions of dollars behind CO2 or hydrogen technology. We're not. So we're not treating it like a crisis.
I think we still have some time, so we can still few questions and comments. Dr. Liao.
Yeah, I also have to add on to what Omar has said. That is exactly true. We should put in more resources, spend more efforts in treating the CO2 problem. And Omar demonstrated a very nice way of capturing CO2 using organic and inorganic matters. The other side of the equation, that's what we are doing, using biological ways. And both should complement each other. We could use organic, inorganic method to capture CO2, then use biological methods to convert it to something that's useful. So those are the grand scheme. Utilizing CO2, don't forget, requires energy, not just capturing. CO2 has basically no energy, and you want to reduce that requires very significant amount of energy. And the only way that I can think of that's scalable is biological, that utilize photosynthesis, that captures sunlight naturally and renew itself. Okay, that's important. Anything that cannot renew itself will become too expensive. Okay, but this is a very important area that all fields of science, chemists, biologists, engineers should work together.
I need to ask the panel members, will you have some last words for the audience?
Yes. Yes, I'm interested about, because for the MAF or Professor Yaghi's research work, we are talking about the absorption of the carbon dioxide or waters or some others based on the metal organic framework. And is there any possibility, or have you ever thinking that use this kinds of MAF as a reactor, like molecular reactors, not just receiving, for example, absorbing the carbon dioxide, and at the same time using the metals as a catalyst, and then simultaneously react directly inside the framework, and then it can become no need to dissolve the carbon dioxide with extra energies.
Yeah, the answer is yes. We published in 2015 a science paper that showed how coughs can trap CO2 and then convert the CO2 to syngas, to hydrogen and CO. Actually, with hundreds of thousands of turnover. But it's still not as efficient. The yield is not as good as you would like. So there's more work to be done. But yes, this is really would be an ideal situation where you not only the MAF can trap the CO2, but also it has catalyst centers that convert the CO2 to something useful. That's why I really like the biological solution that Jim described for the conversion of CO2, because I think a lot of the synthetic systems that are being tried now have a lot of problems. We don't have good synthetic systems, but the biology seems to work very well, and my understanding there's already a plant focused on turning CO2 into high-value chemicals, already an industrial plant doing that.
Well, through this forum, we see the hope that we can solving, not really 100% solving the crisis, but at least a step forward. But we also see the problems of all the accomplishment which need to be monitored or scalable to achieve the goal. So as I said, that this effort, we need all the people and in all fields to try together and work hard toward our goal. Thank you.
Yaghi, you want to have your last word?
I mean, my last word is that I'm really optimistic person. I've lived I have an optimistic view about overcoming challenges. I like to think that I've overcome a big challenge in chemistry that led to the production of these materials, but I also think that I believe in the power of human creativity. We are very creative, and we don't all need to be creative, but few of us are just enough, that it's really a low bar. Just few of us who are creative can make a huge difference. But we have a lot of very smart people who are creative. So as long as society has the will to solve a problem, and not just words, but resources put into solving that problem, it will be solved. Okay? And none of you can tell me that over the course of civilization, this has not been true. Every single time. When society faced a problem, whether it's a health problem or industrial problem, it was solved when those two things came together, the will of the people and somebody, and the society put resources behind it. Why? Because humans are very creative. That's the hope.
It is a very fruitful discussion, and also there are some questions we do not have time to discuss. But I would encourage those who are asking the question, we try to go to YouTube or the Tang Prize webpage to go through Professor Yaghi's laureate lecture. Many of your questions, you can find the answer in that particular lecture. Thanks.
Thank you for this enlightening discussion. And let's invite Dr. Yang for the closing remarks.
Well, the officials of the Tang Prize Foundation has assigned me an impossible mission, asking me to conclude the lectures and the forum discussion in 3 minutes. Maybe next time they should consider to invite Tom Cruise, who can do better in Mission Impossible. But anyhow, I have to dodge myself from that impossible mission, but instead, I will share with you what I have learned today from the both technical side and non-technical aspect. In the spirit of free speech movement of UC Berkeley, you may agree or disagree with me. But however, I think we should all agree to disagree. First, it's an excellent enlightening lecture with a great presentation. Even a stupid chemistry idiot like me now understand what's morph, what's cough. It's something very important. And again, Professor Yaghi's presentation remind me my good days at Berkeley about 35, 40 years ago. And in particular, remind me of my late supervisor, Professor Mitchell. Both of them has demonstrated one thing very important in academic honesty. He's a role model for us for his presentation. You can see the pictures of his co-worker, his students, even his undergraduate student who work on the project. And also, if you are careful to read the reference on his slides, the first author of the paper is that particular student. For professors here, I would like to ask a simple question. How many of you can be that honest in your research result when you are presenting? And many scientists try to answer the questions such as what, why, and how. They do not care about the practicality, cost, ease of operation, so forth and so forth. Quite exception what we see today, Professor Yaghi has spent an effort to make this discovery applicable to daily life. I myself was not trained to be a scientist. I was trained to be an engineer. So I look at those problems very, very carefully. So without Professor Yaghi's agreement beforehand, in fact, I would certainly welcome you to be in the engineering community in the future. So to make better quality to improve the quality of life, that's what you are doing now. I think after today's lecture and the forum discussion, everybody gets richer intellectually. And so today we would like to thank Professor Yaghi for his enlightening lecture and the discussion. At the same time, we would like to thank the Tang Prize Foundation for all the donation, for all the support for this series of lectures. And also I would like to thank the audience. Without you, there will be no Masters Forum today. And there are, last but not the least, we have many, many of our co-workers, our staff member, and as you may see, they are running around behind the scene, the working crew, and so we make this lecture successful. So with that, I would like to pass my microphone back to our master ceremony. She's working very hard today. Our Professor Zhaijun Wu of the Institute of Environmental Engineering at NYCU. Thanks.
Thank you, Dr. Yang. And thanks again to Dr. Yaghi and all the panelists, all the participants today. The 2024 Tang Prize Master Forum in Sustainable Development has now come to an end. We sincerely appreciate your presence and participation today. We look forward to welcoming you again at the next Tang Prize Master Forum. Wishing you all a wonderful day. Goodbye. Okay. Sure, thank you.
So we all stand here?
Yes, stand.